Everyone to the Sussex AI seminar this week. Today we have Dexter, our very own. Dexter did his undergrad studies in Sussex, did a nice JRA, and now is one of the BAI scholars from the Biomimetic and Embodied AI doctoral scholarship program funded by the Lever Trust, and that's why you find these symbols there. And I know that Dexter is also going to introduce himself in more detail, so I'll leave it there. So thanks for coming, and thank you, Dexter.
Thank you, Thomas. Yeah, as Thomas says, I'm Dexter. I'm a third-year PhD student, and today I'm going to go a bit over my background and journey into research, and then some of the projects that inspired me to go down the route and what's kind of inspired my actual research now, and then where this is going to go next, of course, because there's still a year and a bit left to tie it all together. And then finally, just some advice for any sort of new PhD students or wanting to do PhDs, which you're welcome to ignore. This is just basically what I felt, but it's up to you. Your journeys are your own. So I did a bachelor's in computer science and artificial intelligence at Sussex, and through that I became very interested in evolutionary robotics, particularly through the module AIAB, and that inspired me to take a route on looking at the Junior Research Associate, which is a really good scheme of getting undergrads to pursue research and work out whether it's where they want to go. And then I had to balance that, of course, with balancing a degree with a few committee positions, going to societies, and there's the first of a few climbing references at the top. That's the Mountaineering Club, as well as multiple part-time jobs. One of which was PAL, which was a very nice one because I could just sort of finish doing my work, and it's a very short commute to the same lab, and then do a session. I did spend a bit of time in the military working for under minimum wage, very little hours of sleep, which I feel prepared me very well for a PhD. And then I became the head of PAL in 2022, which I've been running since then. And it's a really useful scheme that helps students who are falling behind, just as a sort of a safety net. And some of the activities I got involved with as a postgraduate started off in just outreach. So we'd go into local schools doing Lego Mindstorms. This was particularly important to me because it was a Sussex outreach project that came into my school in Port Slade, Packer, if you've ever heard of it. And very few go to university from my school, so it was very nice, like being able to learn to code. So I initially taught myself to code when I was 12 because it wasn't in the curriculum, but then Sussex came in and really developed those skills further and got it to a standard that we were confident because the school couldn't. So I wanted to give something back a bit and go into these schools doing Lego outreach, robotics, and that was really fun. We got to go into a lot of local schools. There was a few punch-ups in our class because the schools were a little bit rough. But other than that, it was quite fun. And this led me in the direction of a project in Malawi that was advertised in Sussex AI that I thought sounded really interesting. So I went along to that and said, I've done some outreach, do you need an extra volunteer? And they did. And that was really fun, just developing a course in data science and machine learning. So my role was teaching the more theory side of machine learning. And we made this curriculum. We went over in April, I think it was. We spent about 2 or 3 weeks there. And the students were really enthusiastic to learn. So yeah, that was a really fond memory, and I think we did some good out there. It was mainly teaching agricultural students, so no coding experience beforehand. I did get what at least mimicked cholera over there. It was not very pleasant. So yeah, if you do ever go on these outreach projects, just be careful what water you drink. And here's some nice hippos and lions. I actually took those photos. And later that developed to an online course that we led in September time, where students could actually join it from Malawi, and it was actually the PAL team who put together these resources. It's all on YouTube as well, so if you ever have a student or know someone who wants to learn Python, we've got YouTube videos that go with notebooks that self-mark, so it's a resource that is out there if anybody's interested. So now let's get on to research. So I started off, like I said, in Acquired Intelligent Adaptive Behavior, or AIAB, was a module that started to introduce me to genetic algorithms and evolutionary AI, which I really found quite exciting. So one of the coursework, it was the COVID years, and coursework was all in simulation, and I don't like simulation. So instead, I decided to build a real robot that would basically evolve to walk, use the GAGs as some code motor positions, and then based off of where like an accelerometer is, it would tilt and try and walk towards a wall. And after the pandemic, we got to a stage where we wanted to go back to robots, but not necessarily Lego robots, because Lego is well, it's a little bit outdated. Plus, Lego Mindstorms has removed all the support for well, their equipment, which is really annoying. So we developed these Bratenberg robots here. And this was, once again, a kind of fun but very stressful project because we had to build 200 of them. And there was a small team of us putting it together. And in fact, the motor drivers, we exhausted the entire UK supply of this specific motor driver. So we had to start like getting them from all around the world and then updating the library to work with it. Out of this, we developed a circuit Python machine learning library that's on GitHub that will allow like neural networks and regression functions to all run on these very small Python embedded boards. And this is now part of the coursework and the curriculum. And then so in my JRA, I worked on evolved navigation. This is still within all the realm of evolutionary AI. So we've got a 3D printed robot there. It was partly to test whether or not that robot could sustain something. So it uses something called a Jetson, which is like a Raspberry Pi but on steroids. And it's very powerful, but you know, how small and cheap can we make a robot? And as it happens, 3D printing isn't a great way to do robotics because it just wears down very quickly. It's as if it's designed to melt under heat. So the chassis itself broke down many times, but it was fun nevertheless. And we did get some evolved navigation working where it evolved to take in this panoramic image and avoid obstacles. Which once again greatly inspired this idea of navigation and avoiding difficult terrain. And this is where my final year project came into it, working on robots that understood their limitations. So this was made up into sort of like two main areas, one of which is being able to get out of being stuck, and another one is avoiding being stuck. So it used something called a WEG. It's a wheel-leg hybrid. It basically is a single-axis rotation, so it's the efficiency of a wheel, and yet, unlike a leg that uses a lot of energy, it will climb better because it's got these grooves in it. And this is all inspired from cockroaches, believe it or not, because cockroaches have been observed to just run at things and move their legs around until they climb up it. So that was why it was approximated to this single rotation. And cockroaches as well can arch their backs, which is why we had this back bending, which worked really well for the robot. And we used a genetic algorithm to try and encode that. And then the actual navigation side of it was looking at sort of very small, low resolution simulations and trying to put that into the real world. So we developed this Minecraft-looking environment, had a robot that would be randomly put somewhere and it needs to get to a target position. And guiding it is energy consumption, making sure that, so if it goes uphill, it's going to use more energy. So what we don't want, let's say we start here and the other side of the mountain, we don't want it to necessarily go all the way over the top because that's going to use a lot of energy and probably get stuck. And the robot or the agent started to evolve contour following behavior, which makes sense if it's about energy efficiency. And then we crossed it to the real world. So we have this image, a depth sensor on it, and you can see where we compress it to try and match the simulation. Then we have a vector prediction from the model, and the vector is always predicting to try and move away from like rocks and harsh terrain that it will probably get stuck on. And considering that it's learned this behavior from a very low resolution simulation that resembles nothing of the real world, it was quite impressive that it managed to do this. So we ended up publishing this originally in UK RAS, which was in Wales, and then it was asked to have a follow-up conference and us to present again at Taros. So this is in Cambridge. A bit of history about the pub. It's where Watson and Crick presented their paper. It was the only bit of history I knew, and all the Cambridge PhDs who were supposed to take us on a pub crawl decided to go without everyone else. So, and because I knew one bit of history, I suddenly was leading this pub crawl at a conference, which was kind of weird. By this point, you can see there's a trend. I very much like research, and as you can see, so I have a picture of Chris and Andy. I don't yet have one with Phil. You might not have been able to spot it because maybe I'm just really good at editing. But maybe by the end of the year, I'll have a picture of Phil as well. But this area of like evolution as well as navigation over harsher terrains really interested me. And a lot of the literature I was finding was showing me that tactile sensing is indeed sort of the area where at least this field is going. So I started to look at nature, and here's the second climbing reference. So when you're climbing, and I know there's definitely some climbers in this room, you're not always looking where you're placing your hand. You feel the pressure, you feel the strain in your arm, but you're not necessarily using visual navigation to get around that. So tactile sensing at this high level, on a human level, is really important. And this is the same all the way down to insects and arachnids. And crabs even. So crabs have hairs on their legs. They've been observed to move slower over rough terrain, as well if they're moving backwards where there's not in their visual field, they'll lower their center of balance and go much slower. And spiders as well have very poor vision, and at least web spiders do, and yet they're able to move around a web because they can feel their way. A lot of this is down to hairs in the exoskeleton, as well as stress sensing in the joints. So tactile sensing is definitely a key area of this locomotion over rough terrain, whereas visual isn't necessarily, at least in nature. So I came across this paper. This is by Elizabeth, who's actually in the picture of the pub. So she developed this tactile here at Bristol Robotics Lab, where, well, she didn't develop the sensor, but she developed the robot, where it basically has this sensor and it will know like an edge. So it will walk along the surface. There'll be sort of two wooden struts, and it will feel its way across. It will know exactly where the wooden strut is, and it will be able to balance across it. And this is generally as far as the literature went in this area. Most tactile sensing is all a focus on grips and like robot hands manipulating objects. So there's not as much in the way of actual locomotion. So why should this be relevant? Well, robots themselves do need to know what their floor properties are. Even when we're walking around, we're not thinking about it, but we are feeling differences in the surface and adapting our walks to it. So this is a snippet from the Boston Dynamics Spot robot, their user manual, and this costs $74,500. And they say basically it's got all these different gaits, but if it's changing from like carpet to a different surface, it might fall over unless you put the setting in. So you pay all that money and it can't even detect the difference between two textures. You have to manually tell it. So tactile sensing is something that isn't really widely deployed, and yet it does have a lot of benefits. So the tact tip, which I spoke about earlier on this paper, this was developed by Bristol Robotics Lab, but there's a number of different optical methods of doing this. So the way it actually works, you've got this camera and it faces this soft silicon mesh, and this has all these like white dots on it just painted. And the way that these dots move, the camera picks up and we can understand pressure, we can understand texture, and just within sort of this temporal data. There's other methods like gel sight, and I mean, there's loads of different optical sensors, and at these conferences, everybody wants to convince you that theirs is the best, but they all tend to have similar accuracies when you do like a review across them. But as I said earlier, it's all focused on grippers, really. So we decided to start off by developing our own. There was a few modifications made to like original designs just to make it fit better. So we designed our own 3D printed holder that just used fewer parts and just easy to put together. The hardest bit was making the mold. So we designed this model that has all these 2mm diameter points. And then we've got to put silicon in here. We squeeze it together, we leave it overnight, and we've got this silicon mesh. Quite often, though, the silicon doesn't actually come out, or it gets stuck in the point. So it was a nightmare to get an actual one that was basically unbroken. And then we developed the tips themselves. And we filled them with a type of gel. Now, the original gel that the Bristol Robotics Lab uses, and it's sort of the standard in the field, it's quite expensive. It's very soft and sensitive, which is great for manipulation. But as soon as you put like a robot on that, the weight just breaks it. So you can see up there, it's all sort of broken apart. So we decided to use this clear silicon gel, and it wasn't as it wasn't as sensitive, but with some experimentation, we found that we could get the same accuracies as the normal gel. So for this task, at least, for feet, it didn't matter that it was less sensitive. And here's just an example of a regression model we made that tracks the optical markers. It was a nightmare to make because you have to manually label this data. The data set doesn't currently exist. Luckily, I had 6 hours to kill in an airport, so I just sat there labeling frame by frame each point, and there's 133 per frame, and there was many hours of videos. So it did work quite well, and then all the papers also suggest doing this, but the further you go down, you realize you don't even need to do this step, so all of that time was wasted. So how much resolution can we truly get, and why is everyone using high resolution? And this is a question I didn't really ask myself at first. I got very taken away by the literature of the optical world, and they always say high resolution is better. There's never really a reason necessarily why. And currently there's no papers that really compare the resolution of these sensors, at least that I've come across. So it was a question that it didn't come to my mind because nobody else has asked it. And it was only really about a year and a half into my PhD when someone else actually said, so why are you using high resolution? I didn't even consider, I was just sort of following the trend. So we firstly looked a bit at like just decreasing the resolution size and seeing if that affected our models. And it does. So our models, about 20 to 25%, it still gets the same accuracies. Below that, we do really start losing accuracy. Here's just an example of a very low resolution. It's just looking at the difference in frames to find out where it's being touched. And then the robot arm will try and move away from wherever it's being touched. Oh, and just to sort of add before I move on, this is a simulation that was made by others to simulate a tactile. You can see even in simulation, it's really low resolution because it's difficult to make sensors in simulation. The way that they cross that to the real world is they use GANs, which seems quite overkill considering you're adding this extra layer of model in between. This is where we started developing electrical sensors. This was the prototype. It was just some force-sensitive resistors infused in silicon, so the soft body prevents a uniform pressure being added on them, which isn't ideal because you're just going to get the same readings across. Prototype worked well, but you can't really put that on the bottom of a robot foot, and we tried, and then wires start coming unsoldered, which might just be my poor soldering skills. But PCB was the next step. We had these designed and printed, and basically the way they work, they've got a negative and a positive side, and a resistor on that, and we put something called a velostat. So the velostat is just a black plastic material that you can see in the furthest image. And the way that works is the more pressure on it, there's more conduction through the material. And then we can detect that on the sensor, and we know how much pressure is being added on each pad. So we've got like a very low resolution field. So there's, I believe, 15 inputs on each of these sensors, whereas previously on an image, we have tens of thousands or hundreds of thousands of pixels going in. So it definitely decreases the size of the model, but is it as good? Some other things we added as well, especially to the later design up here. So this is what we refer to as the press tip. All it does, it has an accelerometer and a piezoelectric sensor on top of it. So this just allows monitoring of vibration. Both accelerometers and piezoelectric do the same job. Piezoelectric are just a little bit more sensitive, and we wanted to see, well, have them on the same sensor so we can gather the same trials and we can see, can we use one sensor over the other, or does it need a combination of the both? Then we went to data gathering. So this was a very long process, as well as just designing the rig. So the rig is just, it's like, think of like a 3D printer, but instead of printing, it's just dragging a sensor along a surface. The first one, we tried to be cheap and just use like DC motors and whatever was laying around. And it worked for getting like strokes of the sensor, but it didn't necessarily move it in all the directions and lead to a very generalized data set. So down the line, we eventually developed this model, which is actually an old CNC machine that we repurposed to do exactly what we want. Now we can control it in 3 dimensions. So we have the X, Y, and we also have the pressure. So we can gather at different pressures, because if it's just one pressure, as soon as the robot's slightly heavier, will our models actually transfer to that? So we can gather a very robust data set with this, which we have, and that's available online. It's on Kaggle, and it's currently in the review process of the university data sets as well. So hopefully will be a bit more professionally available too. The data set itself, now this is something that always annoys me because there's no standard in the field. Everybody just picks whatever's laying around their lab and that becomes their data set. So we try to be in keeping with what actually exists in these papers, so we're at least trying, it's somewhat comparable, but also materials that represent different services that a robot may come into. I think the bigger data set, the better it will be, but there's only so much time and so many things that I can get hold of. I was even cutting my parents' sofa at the back to get some leather and they weren't too pleased. So before we get on to the comparison of textures, some of the preliminary work we worked with the resolution, and this is the paper that I presented in Cairo quite recently. We wanted to see like how versatile are some of these sensors? Can we do anything interesting with them? So we built this robot, and also I kind of wanted to build a robot. If I don't build a robot every so often, I kind of waste away. So this was one that we built just last year, and it has these tactile sensors, so the big rectangular PCBs. Now they're very low resolution, so you can see on the pictures on the left, this just has a disc underneath the sensor, and you've kind of got a blocky representation of a circle. So we wouldn't be able to use it to say like what different objects are because it's really low resolution. We can at least tell that there's an obstacle. And for a robot walking around, that's good enough. We don't need to know much more. We can also know about different edges. So here's an example. The north just corresponds to the front of the sensor and the south just corresponds to the back of the sensor. So if this is an edge and I've got my hand on it, there's more pressure on the side where there's an actual edge, and then it's empty underneath. And that's what we're seeing here. We've got more pressure, the higher pixels, and then the lower pixels there's less pressure. So this is all very humanly classifiable when we look at it, and knowing exactly where an edge is. And the next bit we want to know, can we actually detect the orientation of the robot? This is another useful aspect to know where the robot is in the real world and how gravity is affecting it, how a slope might be affecting it. So we gathered another data set where the robot would just lift up onto one foot and it just tilts sort of back and forth, recording on an accelerometer the ground truth, so that becomes our label data. And then on the actual floor, we have the pressure on the feet, and that becomes our X data. And this was supposed to be a GIF, in fact, but it for some reason isn't playing, but it's the robot moving back and forth. So we have now two data sets. We have the edge data set, which is just made of singular frames of just different pressures in different directions. And then we have our our tilt data set, and this here has temporal windows. And we found that we couldn't just use singular frames to detect it. We needed some form of temporal input going into the model to actually understand its tilt and to get it accurate enough. And then this is what the label looks like. These are just the accelerometer values. You can see where it's tilting and going up and down. We deployed a few different models for this as well, and some worked better than others, and we will see that in the results. So for the tilt, it worked really well, actually. So it's difficult to see, particularly if you're colorblind, but the green is the y-axis, so this one, and then this dotted red is the predicted one. You can see it's exactly on the predictions. So the robot is very accurately knowing where it's tilting in the real world. And in fact, even in the accuracy, we've got it, or in the loss, we've got it very close. The minimal error, the average error is like very similar. So this is, at least on a normal surface, a good method of detecting it. Of course, we're not trying to replace accelerometers, they exist, but it is showing the versatility of some of these tactile sensors. And the edge detection with a random forest model got 91.8%, so it is quite good at detecting where the edges are. Now with texture, this is where it didn't do as well, and hence leading into the more rigorous and using different sensors. You can see here we've got readings and our predicted values just aren't quite matching. They might be in the general area. There might even be some patterns that it's working out, but it really struggled at detecting these textures. But is this necessarily a bad thing? Because we do want textures to be different in the data. If we're getting different readings, that does show us something. So that's why these sensors then will move forward to see, can we get a bit more from them? Can we actually detect texture rather than detecting orientation? So of course, if a robot is on like a soft surface, it's going to have different pressure values than if it was on a hard surface. And that's not going to necessarily align with what a simple model finds. So our textual comparison study, we used the tap tips, we used the press tip, and we used a number of different values, also a number of different sensors within that. So we used the piezoelectric, the accelerometer, mixtures of the two, and did a big study of like what models perform best and what sensors perform best. There's a lot of data here, but the ones we need to be aware of is the LSTM performed best. which shows that the temporality of the data is at least what models are picking up on and doing better at. However, we're still getting very high accuracies across the board, particularly on the tactiles. So high resolution does lead to better data, whereas the more electrical side, it is getting lower. Indeed, accelerometers do the worst out of the two, but then adding an accelerometer with the piezoelectric gets better than just a piezoelectric on its own. There's some sort of information an accelerometer captures, but not enough by itself to actually be useful. And just to check if there's some generalization across the board, so we gathered the pressures at the pressure ID 68 and 100. So that's just some different forces of gathering the same data and the same movements with the sensor across a surface. And then we try to see, does it actually generalize to unseen textures or unseen pressures? Has the model actually learned what a texture is, or has it just overfit to a specific pressure? So CNNs, they may have had some generalization going on. We can't get the low, and the further away from the pressure that you have, the worse it does. However, the LSTM still performs incredibly high on this unseen data. So we are getting something that is generalizable, at least in the pressure way, which is great when we want to deploy these sensors on a physical robot, because we have no idea how heavy that robot's going to be. And here's just some existing work in the field. And as you can see, and this goes back to my annoyance with some of the data sets out there, we've got so many different textures. And I mean, you've got 92% on the piezoelectric here, and yet it uses 8. And also, do we know, are these textures even similar? Are these textures really far apart and very easy to classify? So there's no standard in the field, which makes it quite difficult to really compare models. I mean, our sense, we've got a larger number of textures, and we're getting some higher accuracies. So you would think, are we doing better? Is that a good metric? But then what if they're using completely like different types of wood where they all pretty much feel the same, there's just slight differences, and we're using a number of different ones? This is one big problem of actually comparing anything. And like I said, so if you have Lego and a sponge, that's going to give completely different readings to like wood and plastic because they're both smooth. And is there something better that we can really do with texture detection? Is there something unifying across? So very few papers have done a move towards friction modeling. And this is a bit better at generalizing the model because friction, or the coefficient of friction, can be used across any data set. So if you have a model that detects the coefficient of friction, it can then be used for slippage later on, but also can be used for yeah, sorry, my mind went blank there. But so the models that we used is we trained regression models. This felt like a regression class because we have coefficients of friction, a number, and that will change based on different textures. So the best models that we used was random forest regression. I've got a highlight that comes up, and that worked best on both the tactile and the accelerometer and piezoelectric hybrid. What we also did, so this trained 1 decimal place, trained 2 decimal places. Let's say the coefficient of friction is 0.98. To predict that is much harder than predicting if it was 0.9. So these models round and calculate accuracy. These models round to 2 decimal places, and anything more, the more accurate you want it to be to the decimal points, of course, the lower accuracy is going to be, because to be very accurate on coefficient of friction is a challenge with these sensors. But we can see if we're just trying to calculate it to 1 decimal place, we can get very high accuracies, in 2 decimal places, slightly less, and beyond that, it does just go down. And this is a problem, but also being able to predict coefficient of friction to 2 decimal places isn't necessarily a bad thing, depending on the task. And the optical, as I said, achieves a much higher accuracy than the electrical sensors. That doesn't necessarily mean electrical sensors are worthless. They still get some good accuracies, and their main advantage is they're much cheaper and computationally efficient. So one of those PCBs I showed you are about £4 each, whereas a tactile is about £100 each. So if you're making a small robot or a cheap robot, or you're on a budget, you might want to use an electrical. And as we did some experiments with like the size of the data set and how that influences a sensor, we found that the electrical does much better with fewer textures, whereas the optical, it doesn't really get affected, at least with the sizes that we've trialed it with. So Electrical aren't necessarily out of the picture, but they are if you want accuracy. And if you are interested in this area, we have a paper which should be coming out, which is comparing both optical and electrical sensors. So where does this actually take us? So let's think back to the beginning where I was talking about robots that are locomoting over different surfaces. And yeah, I've just given a presentation comparing two different types of sensors, where I spent most of my PhD comparing these sensors because we need to pick what one's actually going to be useful and have a good reason to say why we're picking each. We've just started to work on some simulations where we'll have a quadruped in a simulation, and we want it to evolve some different gaits for different surfaces. So we're going to be able to set the coefficient of friction in the simulation. And like I said at the beginning, it's really difficult to actually put a sensor in a simulation and get it accurate or any way crossable to a real sensor. So what we'll do instead, and this is the plan at the moment, and we'll see how well it goes, is by setting the coefficient of friction in the simulation, we bypass the need for a sensor there, and we just assume that the sensors are putting it in. But in the real world, we'll have a real sensor telling us what the coefficient of friction is. So that means all we need to focus on is evolving a gait for these different surfaces. And then, yes, selecting the appropriate gait for that. So if we're on a carpet, then we'll have one gait for that. If we're on a slippery surface like outdoors or something, we'll need another gait. And that's where this is going. Now, before I sort of finish up, as I said at the beginning, some sort of advice to PhD students, and you can ignore it, this is just mine. So PhDs are definitely stressful, and you're probably all finding that already, but they're also long. So unlike in your undergraduate, you don't really get like summer off. It is long. And when you start like working weekends and things, you suddenly lose a lot of time, and you are just suddenly tunnel visioned in your research. And sometimes I'll do like a weekend here and there, but I try and avoid it. And you sometimes see another colleague in the office and you think, you also have a problem. And it's kind of nice to see others, but also you want to be doing a bit more. But also do enjoy the PhD and take advantage of some of the places you do get to go to. So when I go to a conference, I'll probably arrive the day before and just try and see as much as I can, because I'm never going to be able to afford to go back to any of these places. So just try and enjoy it a bit. And that brings us to our final climbing reference as well. So I still get involved in lots of different sports and things just to break up the research. So that's actually climbing Trefan in Wales, if anybody knows. But yeah, just like try and enjoy it. Think like you're still in university. Just utilize what's here, and yeah. But as I said, your journey is your own, so you can ignore all of this and whatever you want. And that's it. Thank you. Yes.
Yeah, thanks for the talk. It's great to see an overview of everything you've been busy. So I was wondering what you think about the potential for fusing, like, even if you say image information isn't a complete description, or can be quite noisy, fusing some amount of image-derived features with information from tactile sensors.
Yeah, it's definitely a very interesting area. So we did think about this, and I don't think there's going to be enough time on my PhD to look into it, but it was going to be like a further thing to look into. I mean, more information tends to be better, provided that it doesn't like overload a model. But them working together, and there are some papers that have done a bit of that, and it does work quite well. But it is not something that I'm too familiar with, though. Yes.
So you mentioned your overall goal was to evolve these different gaits for different surfaces. So there's the idea you're going to detect a surface or a friction coefficient or something and be like, oh, this is the thing we evolved for this category of surface or something. Or is it going to be more like a smooth kind of fuzzy kind of system where it's like, oh, we've got this coefficient and we've got this kind of surface, here's some kind of blend of gaits that we've like somewhere in between that?
Yeah, that's a really good question. And the blend would be much nicer, but it's being realistic to implement. Before I have to hand in my thesis, it will probably be the gait adaptation. So we'll have like 5 different gaits for different surfaces and adapt to it. But I would really like to go down or even just like adapting on the spot would be a better way to go, I think, maybe future work, maybe even a postdoc, but not a PhD, unfortunately. But yes.
Yeah, I had a question about your regression work on the friction coefficients. So it felt to me as if you were actually treating it like a classification problem in the end, where basically said, oh yeah, to one decimal point accuracy, I'm going to look how often I hit exactly the right number, right? Is that not what you did? And
It did end up being like that in the end, yeah. So it started off with the hopes of regression because it makes sense with like different numbers and it would regress across. But then there was a bit more of a non-linear relationship. The regression model was treated in this way, you still got good accuracy, but yeah, it did end up kind of becoming more classification because of the way that we were rounding it.
so what was the disadvantage of doing proper regression? So like basically just measuring what you predict, the distance between your predicted value and the
It just couldn't get
Yes.
decimal accuracy on these. So let's say it's like 0.98746 or whatever. It's just not going to be able to predict. 'Cause there's so many different values. It will maybe get it in the general area, but it can't get it to the decimal point that we want.
To put that a different way, isn't that just what the MSE measure is going to show you? Like when you do a regression, the MSE is going to be a
mean squared error.
Yes.
Yeah. So that's
Initiated.
yeah, that could be used to show how well or how close it's getting at least. But then I wanted to put it in terms of accuracy, mainly because when I was in Cairo, some professors started telling me off for using just loss instead of accuracy. So I didn't want to make the mistake again.
Yeah, okay.
And you could just
No, I understand.
error, for example. That's basically would show you the decimal placing directly.
Yeah. Yes.
In terms of like developing your gates, like what kind of, are you gonna like hand tune them, or are you gonna do a reinforcement learning approach on different surfaces, or yeah, what was the plan for like developing those?
So we're currently looking into CPGs mainly through like CTRNNs, because it's got a lot of success, at least in the field, and at least in early evolutionary robotics. Although I like to use a GA, I think reinforcement learning is a bit more realistic for this task because it's not a simple one and there's a lot of parameters that need tuning for this. I've done some preliminary work before I was using the CTRNNs, just doing some reinforcement learning, but on all motor joints. Of course, the search space was really big and the robot just ended up sort of cheating the simulation. It would just like hit its legs crazily into the floor and then just fly off. And then it would end up getting a really high score.
I also have a very primitive question. Do you really need to fill those tuck tips, or could they just be full of air? Stiff enough.
So the problem is if they're full of air, as soon as you put it on a surface, they just like move inwards and there's not much movement. It's like a
They're too soft, so to
shape, and then you put a surface, it kind of goes like that, and then this kind of moves a bit, but it doesn't move. It's very constrained compared to when you have like a gel in and it only pushes a little bit and you can see the way that they will move with like vibrations.
So is it not equivalent to making it stiffer? Like leaving the gel away, but just getting different material that's a bit stiffer.
I haven't actually tried that.
Or like thicker, I guess.
Do that, yeah, especially like 3D printed flexible materials. We played a bit with them, but they're really like difficult to print. But it's definitely a direction you could go in, yeah.